Excuse me. So first, let us take a look what we have learned last time. We have learned we are getting when we investigate into the quadratic rules to approximate the integrals, and then the first things we learn is the simple trapezoid rule and then simple Simpson's rule. And then later on, we in the last week's lectures, we learned how to create the composite trapezoid rule, composite Simpson's rule to get better approximations to the integrals. And actually, you have several homework questions related to the composite rules, and also we show one examples here, and then we use the coding things to show that the for these examples, if we use the composite Simpson's rule and then compared to the simple one, we have a more accurate result. And so today, we would continue our discussions on the integrals, and then, but this one is not the Simpson's rule, not the trapezoidal rule. We call it Gaussian quadratic rule. And so let's take a look at what we have here. So before this is a general descriptions on the quadratic rule. We have the Lagrange polynomial here, and then we have endpoints x0, x1, and xn minus 1 on the interval a, b. And then we have, because we have endpoints, and then we can have the n-1 degree of the interpolating polynomials of the f. And then this is the n-1 degrees of the polynomial. And so we express the Lagrange form in this way. And if we do the integrations, this is the general form for the quadratic rule. And then if we do the integrations here, and then we got such a quadratic formulas for that to approximate the integrals. And this is something we have already investigated into. And let's take a look at here. For the trapezoid rule and the Simpson's rule, and or the composite trapezoidal rule or the Simpson's rule. And if we want to place all these nodal points on the interval AB, and we just put it into, we just let them equally distributed, which means that we have for the subintervals, and then for each subinterval we have equal length. So we have, if we have if we have 6 intervals here, and then for each interval we have the step size is the b minus 8 divided by 7, right? And this is equally distributed for the points, for the nodal points. And so, but actually in this quadratic rule, you will see that, okay, we have fxj, and then this is the basis functions here. And actually you will find out that this xj is also a component in this format, in this formula. So what would happen if we choose the nodal points not equally distributed? So if we put it to another places, maybe in this way. So let's take a look at here. So this one, this is the trapezoidal rule, right? And then we take the endpoints to be our the representative point here. And then this is the trapezoidal rule. And then let's take a look at the figure 2. the figure 2 here, we are going to choose some points, not the endpoints, and then that is some points inside the interval. And then we are using, we are connecting these 2 points and then to be the straight line here, and then approximating the intervals with this trapezoid here instead. But not the endpoints, we use the some points in between the interval AB. And for this examples, we do the same things. We choose other learner points in between the A and B. And if you compare to the trapezoidal rule, you might find out that in the figure 2, we might have a better approximations. So if you take a look at the, let us just focus on the first picture. And then you will find out that the difference between the exact result and the approximations results is this one. This is the missing part, or this is the error part, right? And then let's take a look at the other method. We choose other nodal points here. And then what is the error? The error should be this one. The blank, the white space here, and then also some, and then minus the extra part here. So the green part minus the red part here. This is the extra part here, and then minus this part, and then that's the error. And compared to, if we compare this 2 graph, and then and it looks like that we would have a better approximations here. So this inspires us to choose the points, the nodal points smartly, and not just use the equally distributed points. And so, but before we investigated how the nodal points distributed, and then we are going to take a look if we have n nodal points, and then how good could we get, how good is the approximations can be. And so if we have n nodal points, actually we can have at most 2n-1 degree of precisions. And this is the most precisions we can have. And let's prove this. So if we have n nodal points, and then n nodal points, we have x0, x1, x2 to the xn-1. This is not true. This is just the quadratures one there. And then and the degree of precisions of the interpolatory quadratures is less than 2n, which means that we have at most 2n-1 degree of precisions. So let's prove this. So this should be the first, the quadrature rules here. So that's the things we are proving this. We are proving if we use that quadrature rule there, and then we can have at most 2n-1 degree of precisions. So let's see, what do we have here? So you already have learned the math A, and then we know that we can, if we want to prove something, actually we can use the proof by contradictions. So it says the degree, the theorem is saying the degree of the precisions is less than 2n. So what we are going to suppose, we are using the proof by contradictions here. So here, the technique we are using is the proof by contradictions. Proof by contradictions. And so let's say, suppose we have the degree of precisions, because the theorem is saying it's less than that 2n. So let's say the degree of precisions k of the 1 is greater or equals to or equals to greater than or equals to is greater than or equal to the 2n. So let's take this, let's take a polynomial here. Let's take this function and then take the f function fx equals to x minus x0, because we have nodal points x0, x1, x n minus 1, right? So let's create such a polynomials. And you will see that the degree of the functions, degree of the fx equals to, because here we have degree 2, and then this is degree 2, and then we have n expressions here. So we have degree of x, fx is 2n. So the theorem is stating that the degree of precision is less than 2n, but here we have a function of the functions with degree 2n. So if we apply the quadrature rule here, and then you will see this so in this quadrature rule, and then this wx is the wave function, just the wave function for the integrals. And so now let's do this. If we are going to do the integrations with that wave function, so usually we take the wave function as wx equals to 1. So usually we take the wave function as 1. And here, if we use this, we would have, if this happens, if this one is exact formula, right? And then we are using this is the first formula. This is the quadrature rule. And then if we use that formula, and then that is the AJ xj, and then the AJ is computed in this way. And this is the AJ looks like. That is the basis function integrals, the integral of the LJX, the basis functions on the AB, and then with the wave function. And this is the AJ, and then this is the fxj. And then what is the fxj here? If you substitute the xj into this function, so what can we get? If j equals to 0, that is, we have x0, right? So starting from j equals 0. And then what do we have? If we substitute x0 here, we got 0, right? And then for the next term is j equals 1. And then we substitute into xj, x equals to x1, and then x1 is 5 this time, but x1 minus x1 is 0, right? Which means that for all fxj here, it equals to 0. So this times, if you are doing the sums for this, all the sums, and then this times is just 0. The sum is 0. So this is because from the definitions of the fx, and then we have fxj equals 0, and this is the reasons why we have that integrals if we apply the quadrature rule, and then we have this one. So this is if we apply the one that is the quadrature rule, and now we got this. But if we calculate this integrals, wave function should be positive, and it's also wave function is just positive. So let's calculate this integrals. So, but on the other hand, what do we have is, so on the other hand, the exact value or the true value of the integrals looks like this. So we have, what's the function of the fx? It's defined with n notables, and then it's x0 squared, minus 1, and then x minus xn minus 1, and then that's the n notables. And let me move this to that. So could you tell me one thing about these functions on the intervals? So for this functions on the interval, and then it should be the negative, right? Because we have square here. And then also we have points where that is positive, right? So if you are doing integrations for this functions, and then with this wave function is always positive, which means that this is a negative function, and then at somewhere, and then this is also continuous function, and then at somewhere it is positive value. It has positive value, right? And this means that if you do the integrals, and then you would get this integrals should be bigger than 0. Does that make sense? Because it is always non-negative, but it is not always 0. And then it is a continuous function. So this integrals is bigger than 0. So we have some contradictions here. If we apply the quadrature rule, and then we got 0. But if we look at the integrals itself, we get this integral is bigger than 0. And what does it mean? It means that we have contradictions, and then this could not be true. So which is the contradictions? Why do we have such a contradictions? That's because we have assumptions at the very beginning. We assume that the precisions of the k can be greater than or equals to 2n, and then here we set the functions to the degrees of 2n, and then we say this quadrature rule does not work, and then which means that we have to say, therefore, the degrees of the degrees of precisions here, the degree of the precisions should be less than 2n, and that's the conclusions we have here. And this is one thing we are preparing to the quadrature rule, and then this is one fact about the quadrature rule as well. We are preparing for the Gaussian quadratures, and so here we have n notables.
So to clarify, the contradiction was that we had a 2n degree polynomial, but we had a quadrature rule with precision of degree 2n or greater. It should have been exact, but it wasn't. Is that the contradiction?
The contradiction is that we suppose we have the degrees of precisions greater than or equals to 2n, and then so let's say if it is 2n, right? And then if you substitute the polynomial with 2n, right? And then you should have exact formula, right? So if it is exact, and then we should have this one from the quadrature rule, and then this one it equals to the exact value. But here the contradiction is that we do have these two values that's not equals to each other. So that's the contradictions. We suppose that is the precision is 2n or greater than 2n, but we don't have such a precision here. And so this is the conclusions. We have n points. So don't forget that at this moment, we are using the index from the x0 to xn, but later on I'm going to change the index because I'm using two textbooks here. And questions? Fxj is 0, right? That is because if we are doing this gamma sum here, right? And then which means that j is equals to j equals 0 and then n minus 1 to the n minus 1, right? So let's substitute this. So we have defined the functions looks like that. And then, so because if we suppose the precisions, the degree of precisions is 2n, right? And then if we substitute any polynomial with degree of 2n or less than 2n, and then the quadrature rule should be exact, because that is the definition of degree of precisions, right? And then now we define this function, and then we substitute the xj into n. So for example, the j equals to 0, and then we got x0. And then if we substitute this function, this value into the x, and then you got x0 minus x0, and then square. X0 minus x1 square. And then x0 minus xn minus 1 square. And then you'll find out that this one is 0, right? Does it make sense? We do the substitution here. We do the substitutions, we have the fx functions here. And then we do the substitutions, which means that we replace this x with x0, and then x0. So we have this. And the x0 minus x0 is 0. Does it make sense?
Is that the fx function, is it like random function?
This fx functions is defined, it's just created for this proof. And then because this is going to be 2n.
Oh, so we're just doing it for this exact function.
Yeah,
Oh, okay.
just put into that exact functions. Because this is the proof by contradictions. Once you have one counter examples, and then you can just say this is a contradiction. So we create such a function here. And then you substitute the xj into this specific function.
So just to be clear, that you're not saying that the quadrature rule has this precision for all functions, it's just for this exact function.
Yeah. It's for just for this function, and then because this is proved by contradiction, so we just need to have one counter examples questions.
So you're gonna test us on this 10th problem on the test?
Test?
Are you gonna test us on this 10th?
I don't think so. This is just like I think the text problem will be easier than this one. So, but this is some conclusions you can memorize with n node points, and then we could have this is n node points, and then we have at most 2n minus 1 degrees of precisions, and then we are going to use this conclusions to look for the Gaussian's quadrature rule. So let's take a look at what we have in the simple, the trapezoidal rule and the Simpson's rule. So let's go back to here. So now we know that if we have n nodal points, right? And then what can we get? At most, we can get at most 2n minus 1 degree of precisions, right? And then, but now let's take a look at what we have learned before. We have trapezoidal rule, and then this is the trapezoidal rule, and let's take a look at is degree of precisions here. Degree of precisions here is should be less than is equals to 1 and less than 1. And so this is the 1 degree of the precisions. But how many nodal points do we have there? We have x0 and x1, so we have n equals to 1 over. We have 2 nodal points. We have 2 nodal points actually. So we have 2 nodal points, And then, so let me erase some things. So here we have n nodal points, and then we can have at most 2n minus 1 degree of precisions. But here we have, what do we have? We have trapezoidal rule, and then we have 2 nodal points. And then we only have 1 degree of the precisions. And then what about the Simpson's rule? The Simpson's rule, we have 3 nodal points. We have the both endpoints and then the middle point over there and the Simpson's rule. And then we have n equals to 3, and then we have 3 nodal points. And then what about the degree of the precisions? We only have 3 degree of the precisions here. So compared to what we have in the conclusions we just derived, and then for the, if we have 2 nodal points, actually we can get at most 3 degrees of the precisions here. And then for the Simpson's rule, it has 3 nodal points there, over there, right? And then if we take a look at what we derived in that theorems, we can have at most 3 nodal points, and then we have at most 2 times 3 minus 1, and then which means that we have at most 5 degrees of precisions here. And believe it or not, and then this is because we choose a wrong set of the nodal points, and then it leads to lower accuracy. So now what we are going to do is come back to here. We have, this is not the satisfied result, and then because we want this degree of precision here, degrees of precision here, we want higher degree of precisions. And then so what can we do here? What can we do? We can do this. We can go to the Gaussian quadratures, and then the Gaussian quadratures, the key to the Gaussian quadratures is to choose the nodal points. So choose the nodal points smartly, and then so we can choose some nodal points in between the interval, but we are not sure how to choose it at this moment. But let's see, let's take a look at this sample 0. So we just calculate that with 2 nodal points, and then we can have at most, so if we have 2 nodal points, right? And then we can have at most, we can have at most 2 times 2 minus 1 degrees of the precisions here. So which means that if we substitute the functions, the polynomials, apply the polynomials with degree at most 3, and then that quadratic rule should be exact. So now let's choose the xi first, and then also with the xi, we need to decide the ci here. The ci is the coefficient, and so we need to decide the nodal points and the coefficients here. And now we are starting using the index starting from x1 to the xn, and then we have n nodal points here, and then we expect that we have 2 times 2 minus 1 degrees of precision here. So let's derive that formula, which has higher accuracy here. And so here we have such an example here. We are doing the integrations on the interval -1 to 1, and then for the functions f. And then let's decide because this is the quadratic rule, right? And then if we expand it, because we just have 2 endpoints here, and we just have 2 terms here, C1 fx1, and then plus the C2 fx2. So now we have 4 variables. We need to determine that is a C1, and then a x1, C2, x2. This is the coefficient, and this is the nodal points between the -1 and 1. We need to decide the values of these things, and then such that this is a formula. And so now let's see what can we have? So we want to get the most of the degree, the highest degrees of precisions with two notables. And then from that theorems, we know that the highest degrees of the precisions we can get is the 2 times 2 minus 1, and that is a 3, which means that if the fx is the polynomials, with degree 3 or less than degree 3, this is a polynomials with degree 3 or less than 3, and then so this is A0, A1, A2, A3. That is just the coefficients for that polynomials. But if we apply this fx functions to that quadrature rule, and then it should be exact. If we expect this quadrature rule has the degree of the precision 3, then if we put in this fx functions into that quadrature rule, then that should be exact value there. So which means that we are going to derive the C1 and C2, and so now we are going to get the C1, C2, X1, and the X2. And these two things is in between the -1 and 1, because we are doing the integrations on the -1 and 1. And then we have the degree of precision 3. And so if we plug in the f functions, and then this quadrature rule should be exact, which means that if we plug in that functions fx dx, and then it should be equals to the C1 fx1 plus C2 fx2 if the fx is a polynomial with degree 3 or less than 3. So now what's happening here? We can use Sarah's, so from that, so the fx is a polynomial with degree 3 or less than 3. So now let's try some things here. We try out the basis functions we have here. So let's try out fx equals to 1. That's just a constant one. And then fx, and then equals to the x. Fx equals to the x squared, and fx equals to x3. So let's just apply this quadrature rule to this set of the function, because this is the basis function for that polynomial with degree 3 or less than 3, and then this is the basis functions. This is with degree 0, with degree 1, degree 2, degree 3, and then let's do the plotting there. So if we do the plotting, we apply the quadrature rule, and then we expect that the quadrature rule is exact, so we have the equal signs over there. So now let's do the plotting. So the left-hand side we have, -1, 1, and then integrations here, and then equals to the C1. So this is the coefficients we don't know at this moment, but let's plug in the x1 into this function, and then we got, because this is a constant function, so we have times 1 here. So this value of the function, it should be 1 here, and then next one is the C2, and then if we plug in the x2 to this function, and then it is still 1. So it times 1 here. And so this means that on the right-hand side, we have C1 plus C2. And then what about this integrations here? And this integration here, if you do the integration, and then it should be equals to, this one equals to, let me see, this one equals to 2. So we have the first equation here. We have the C1 plus C2, and then equals to 2. We have the first equation, and then you are going to see 4 equations here, and then we have 4 unknowns to solve. We have the C1, C2, and X1, X2, but we have 4 equations, 4 linear equations. So with these 4 linear equations, we can solve 4 variables. And so the next things is to plug in the fx equals to x, the linear functions, into that quadrature soup. We are going to do the integrations here, integrate from -1 to 1 and the x dx. And then, so if we do the plug in here, plug in the x1 into here, and then we got this. We got the c1 and then times x1, and then c2, and then plug in the x2 here. Fx2 equals to x2. So here we have x2. And this is the right-hand side. This is the right-hand side of this equation. And then for this one, this is a definite integrals. And then we can do the calculation here. And then the calculation, after some calculations, we could you get the values on the left-hand side. And then this is equals to 0. And this is the second equations we get. So we would do the same things for the third equation and then fourth equations. We do the integrations here, -1 and 1. We are applying this quadrature soup. So for the left-hand side, if we put in the fx equals to x squared, and then we got this, and then equals to, and then on the right-hand side, it equals to the c1 times the x1 squared, and then c2 times the x2 squared. And then once again, for this definite integrals, and then its value, up to the calculations, we got this is the 2/3. And this is the third equations we get. And then for the fourth equations, we would do the same things. -1, 1, x cubic dx, and then because this is the odd functions, and then if you do the integration, and then it's still 0. And then equals to c1 times the x1 cubic, c2 x3 cubic, x2 cubic. So now you got 4 equations, and then 4 variables. This is not linear equation because we have x1, x2 cubic here, square here. But you can solve these equations with the Python or some algebra knowledge. And then after solving these equations, you would get this. So solving this system of the equations. And then we get this. We get the C1 equals to 1, and then C2 equals to 1, and then X1 equals to the negative square root of 3 divided by 3, and the X2 equals to the square root of 3 and then divided by 3. And with all this in mind, and then we got this. This is the Gaussian's rules with 2 Gaussian's quadratures with 2 nodal points. And it can be approximated by, so because we have the coefficients 1 here, so I will skip the writing of 1. And then we have the nodal points, negative square root of 3 divided by 3, and then square root of 3 divided by 3. This is -1, and then this is the positive 1. And this is the quadrature rule, Gaussian's quadrature rules on the intervals. This is the Gaussian's quadratures on interval -1, 1, and then with 2 nodal points. With 2 nodal points. Does it make sense? So we just do the plotting here, and then so for the C1, C2, X1, X2, because we expect that the highest degree of the precisions, we just investigated into this theorem, and then this theorem tells us that the quadrature rule, the interpolatory quadratures has at most 2n minus degree of the precisions if we have n notables. And then so for the Gaussian quadratures, we want the highest degree of the precisions. And then for here, we have just two notables, x1 and x2. And then we need to find out the x1, x2 location, and then the c1, c2, the c1, c2 coefficients corresponding to that notables, so that we have the highest degree of the precisions. And then the highest degree of precisions here, because we have two notables, and then that highest degree of precision should be 2n minus 1, and that is 3. So by the definition of the degrees of precisions, we can substitute the x equals to f equals to 1, f equals to x, fx equals to x squared, up to the x cubed here. And then we got 4 equations, and then so for 4 variables. Any questions here to get the simple version of the Gaussian quadrature rule? Actually, you have one homework in your assignments. That is the homework 1, right? The homework, the question 1. And then it is also asking you to find out the coefficients over there. You just need to plug in the polynomials and then solve their equations over there.
It works fine for like more than 2 number of points, right? Like 3, 4, we can still apply this to find. Like,
Yeah.
the one with the highest degree.
Yes. If you have more notables, then you can also find it in this way. But actually, for the Gaussian quadrature rule, the points are fixed. They have the fixed locations to get the best approximations. So you will see this in a moment. So I will not ask you to, maybe I will ask you to do to calculate the C1, C2, X1, X2 in the simple situations. I will not ask you to calculate n equals to 5, n equals 6. That is crazy, so crazy. But one good news is that for each interval, the Gaussian nodal points, the locations of the Gaussian nodal points are fixed. And so now we go to the general way to get the nodal points and the Gaussian nodal points, and then derive the Gaussian rule here. So we just say the Gaussian nodal points are fixed, and then how it looks like, how they look like. Actually, the Gaussians, have you learned the Legender's polynomials before? And actually, I have to tell you the news that for that Gaussian nodal points, the good news is that, so if we have n nodal points, and then that nodal points, the n Gaussian nodal points, it could be this is Legendre polynomials, and then the Gaussians. So I just write down here. So the good news is that the Gaussians nodal points. So I'm talking about the intervals -1, 1 at this moment. And then the Gaussian nodal points are the roots of the Pn. So assume that we have n nodal points, and then the Gaussian nodal points are actually the roots, that is the zeros of the Pnx, and then the Pnx here is the Legendre polynomial, the n Legendre n degree n Legendre polynomial. So the Legendre polynomials are unique up to a constant, and then so because it is unique, so you will see the Gaussian nodal points are unique as well. So this is something we are going to talk about in this section. And so this is a simple examples to calculate the Gaussian quadratures. But here we are going to use the Legender's polynomials to derive the theorems below. And then that is the theorems about the Gaussian quadratures. That is just one simple examples, but here we're going to use the Legendre polynomials to derive all the formulas for the Gaussian quadratures. So we are going to use the Legendre polynomials here to get the nodal points, the Gaussian nodal points. And one of the best things about the Legendre polynomials are that they are orthogonal polynomials, which means that, so we have the P0, P1, Pn, x here, and then this is the Legendre's polynomials, right? And then from the definition of a Legendre polynomials, and then you know that how to generate the Legendre polynomial, right? We use a basics here. This is the basis for the degree n polynomial. This is the set of basics, 1, x, and then x2, and then x3. And then how can we get the Legendre's polynomial? Let's say we have the n degrees of polynomial here, and then these are the bases. And you will use the Gram-Schmidt process, and then to get Schmidt process to get the Legendre polynomials. And then the Legendre polynomials we have, what is the Legendre polynomial here? We have several good, just one very good quality here. We have one very good feature here for the Legendre's polynomial. And then, so let's say we have the P0, Pn. So let me just write there. This one would be more clear. So we have P1s, P0s, P1, Pn here. And the properties for this one is that the inner product between two polynomials, Pnx and then Pmx dx, the inner product of them are 0. And when the n does not equal to m. And this is the definitions of orthogonal, which means that their inner product is 0. This is the same thing as the algebra class. The orthogonal, it means that the inner product equals to 0. But here we have polynomial, we have function. The inner product is defined in this way. It's the integral of the product of two functions. And this is the best properties we have for the Legendre from the Legendre's polynomials. So here, from here, we also have these two properties for the Legendre polynomial. So for the Pnx, and then this is a monic polynomial, which means that for the highest degree here, highest degree term here, the coefficient should be 1. So let us say the first few Legendre polynomials here, you will see this is the highest degree term, highest degree term here. X, x2, x3, x4, and then they are with the coefficient 1, and then that is what we mean here, the monic polynomial. We have coefficients 1 for the highest degree term in that expressions. And for the second, this is second property here. So the Px is a polynomial of degree less than n, and then the Pnx is with degree n, right? So why do we have such a property here? So this one is with degree n. This is with degree n. This is the Legendre polynomial with degree n. A Legendre polynomial of degree n, and then the Px. The Px is a polynomial of degree less than n, and then the Legendre polynomials is also a basis for a set of basis functions, and which means that the Px, because this is the polynomial, it's a polynomial of the degree less than n. And then also because the Legendre polynomials can be a set of basis functions for the for that Plano's functions, which means that we can express the px in this way. It's with the a0 p0 x and then a1 p1 x and then plus the a2 p2 x and then plus all the way to, because the degree of this polynomial is less than n, so we can have the basis functions up to the Pn minus 1. This one is with the degree n minus 1. So we can also express the px in this way, but the a0, a1, a2 are the coefficients for these basis functions. And so as we have such things here from the Legendre's Plano's property, and then if you do the integrations between them, if we are calculating the integrations between f-1, px, and then pnx, and then what do we have? We are going to do the integrations between the a0, p0, x, and then pnx. So we have the sum here, right? And then so, which means that, so we have the px. So this is px. And then all the way to the an minus 1, pn minus 1 x, right? And then times the pnx. And this equals to, it actually equals to, if we split the sum into several integral, and then it equals to the a0 is just constant, and then let's move this out, and then it's just p0x, and then times the pnx. I'm just expanding this expressions by multiplying each term here, the p0x times the pnx. And x here, and then plus the a1, and then here a1 p1x the p1x times the pnx dx, and then all the way to the an minus 1 integration 1 pn minus 1 x, and then the pnx dx. And you will find out that for each term here, the 0 does not equal to n, 1 does not equal to n minus 1 does not equal to n. And now from the basic properties we have for the Legendre polynomials, we have the inner products equals to zeros when the n does not equal to n. So for this inner products here, this inner product, this integrals here, they are all zeros value here. Does it make sense? Because p0 does not equal to pn, 0 does not equal to n, 1 does not equal to n. And so from the basics, this is orthogonal polynomials. So this inner product should be 0. This inner product should be 0. This inner product should be 0. Does it make sense? Because they are orthogonal. They are orthogonal, right? So this is 0. So these are 0. That's why we have 0 here. So we have two very important property here, and now we are going to make use of this property to derive the general Gaussian quadrature rule. So we have just investigated into two nodal points, and then that's the just one basics. So in the example 0, we investigate into, we have two nodal points. So what if we have n nodal points, and then how can we choose the n nodal points for the Gaussian rules? And if we have no n nodal points, and then how would they distribute it? And then how does the quadrature look like? So the quadrature rules, so the first things you need to choose the xi, right? And then the next things you also need to decide the ci, the coefficients as well. So what does that mean here? I mean, I'm going to figure out, because I have the quadrature rule here, And then I want this to be exact up to the degrees of precision. That is the maximum degree of precision. We want this has the maximum degrees of precision, which means that we want the degrees of precision equals to 2n minus 1. And if we want to know what this projections look like, we need to decide the CI value, and then we also need to decide the XI value. So next, if we have n notables, what does the CI looks like? What does the XI looks like? So next, this is the 3M2, and this is a 3M2, and then this is the projections rules for the n notables. So let's take a look at the statement first. So this theorem tells you that for the Gaussian quadrature rule, and the n notables are decided in this way. They are the roots of the nth Legendre polynomials. And so now we know the positions of all the n notables. They are the roots of the n Legendre polynomials. And for the CI in the quadrature rule, it is defined in this way. It's the basis functions, the intervals of the basis functions over the interval -1 to 1. So we are still talking about the integrations over the interval -1 to 1. This is the basic situations. So with all this in mind, we have already decided the xi here. The xi, the notables are the roots. And then the CI is just the integrals of this basic function here. With all this, and then we get a projections rule, and that degrees of precision is 2n minus 1. And this is the projections rule. And this sentence is telling you that, so if Px is any polynomial of degree less than 2n, and that this projections rule is set. And then which means that the degree of precision for this projections rule is 2n minus 1.
What if the polynomial have more than n roots?
What about the polynomials have more than n roots, right?
Oh, okay.
That is the Legendre polynomial. The Legendre polynomial is Pn, and then it is with n degrees of
Okay.
the n Legendre polynomial is with degree n, so it has n roots. It just had n roots.
Could it be have like repeated roots?
Actually, it would not. They would not have a repeated rule, and then there's one more property about the Legendre polynomial. If you solve the Legendre polynomial, there is one very good thing about the Legendre polynomials. And then the Legendre polynomials is orthogonal, right? And then if you solve the P and X equals to 0. And then, for example, so we have, this is n degree of the, this is the polynomial with degree n. You will see that the roots here, this is the origin to 0, right? You will see if n equals to 2. And then this is the interval -1 and 1. This is the integrations. We are doing the integrations over -1 and 1. If you solve n equals to 2, this is the P2, the Legendre, the second Legendre polynomial. And then if we want to solve this, you will find out that two roots is symmetric about the origin, the origins, right? This is the roots here. This is the roots about for the P2 here. And then you will find out that for the P and X, you will have the same things. And so for the P3 X, you have different roots, but so the first root you have here is 0, and then you have one root here, and then maybe it's the R1. This is the first root, and then it's 0. And then you have another root R1 here. But you would definitely have another root that is symmetric to that origin, and then you will have a root here as well. So we will not have repeated roots. They are symmetric. And for the odd numbers, odd index polynomial, the gender polynomial, you have the 0. But if you, this is a E1's index Legendre polynomial, and then that is, there's no 0 here, but never repeated.
Could there be complex roots?
Hmm?
Could there be complex roots?
Complex?
Yeah, because a polynomial might have complex roots.
So that can be here.
If you, I mean, a polynomial might have complex roots, right? So
Yes, but
if you
this
have
one
many
has
roots,
only-
some of them might have complex.
But this Legendre polynomial has only real roots. Yeah, you can prove that. They only have real roots in on the x-axis. And I believe that we can see this in the. Actually, you can prove that. I would not spend the time to prove that, but I would tell you the truth that for the Legendre polynomials, and then they have real roots, and then also the roots are symmetric. This is one property about the Legendre polynomials. But if you are interested in it, and then maybe you can Google it and prove it. But this is just one fact we need to know. But it's good to consider the complex root as well. It's really a good question. What if it has a complex root? But here for the Legendre polynomials, we do not have the complex root. We have real roots. So, so this is theorem 2. And any other questions about the statement? So let's just say, okay, let's just also write down the roots. The roots are symmetric about the origins. The origins 0. And then, so don't forget that we are doing the integrations for the, we are approximate the integral here. We are approximate the integrals on over the integral -1 and 1 for this theorem. We are still investigating into the basics version. So let's see why this is true. Why do we have the degree of precisions less than 2n? The degree of precisions equals to 2n minus 1. So let's take a look at the basic situation first. So let's see the basic situation here. Situation. And then this basic situation, the px, is with degree less than n. It's a polynomial. And so let us rewrite the terms into the, rewrite this term, rewrite the px in terms of the n minus 1 Lagrange polynomial. So we have n notables, and then we can write this into the n minus 1's Lagrange polynomial with the notables. With the notables, the notes at the roots of the n Legendre polynomials. So which means that we have, so first we have already decided the nodal points positions here. They are the Legendre polynomials, the roots of the Legendre polynomials here. And then if we have a basic situation, and then the px, that is the function fx. And then we let the px is with the degree less than n, and then we can rewrite these functions into the n-1 Lagrange polynomials, because we have n nodal points here. So we can rewrite it into the n-1 degrees Lagrange polynomials with n nodal points here. So we have n nodal points from the Legendre's polynomials, and then we do the Lagrange interpolations between this among this n nodal points, and we have one. So from the Everton for this Lagrange interpolations we have. So if you go back to the chapter 4, chapter 3, and then you would get this Evertons for this Lagrange interpolations. And the Evertons, it looks like this. And so we have the px here. And so we have pnx, that is the n derivative. And then it evaluates at somewhere, that is a cosine x. And then the cosine x is in between the n factorial, and then cosine x is in between the a and b, -1 and -1 and 1 here. And then x y minus 1, and then all the way to x minus x2. And then all the way to x minus xn. And this is the Evertons for the Lagrange interpolations. We have one polynomials, and then this polynomials is less than degree. The degree is less than n, and then we are going to do the Lagrange interpolations among this n nodal points, and then the n nodal points is decided by the roots of the n Legendre's polynomials. And then we have such an Everton, and this is n derivative. But what do we have? We have a polynomials that is less than degree n, which means that, so because the px, the polynomials we are considering is of the degree less than n. So the errors is 0. Does it make sense? Because this is the Everton for the Evertons for the Lagrange interpolations for n device, and then because we are considering the polynomials that is less than the degree is less than n, so if you take the derivative here, and then this derivative should be 0, because the degree of the polynomials is at most n minus 1. So here the error is 0, which means that this representations, this means that the Lagrange interpolations here is exact. So we don't have error, so which means that it is exact interpolations here. So now let's go to the representations. We can write the functions in this way because we have the Lagrange interpolations format, and then we can rewrite it into the Lagrange interpolations format. We have n nodal points here, I equals to 1, and then that is x1 to the xn. And then this is the Lagrange interpolations format. So this is the Lagrange interpolations for the px, the function px we are considering, and then the px is with degree less than n. So now we can write more things about this interpolations. So we have sigmas n I equals to 1 pxi, that is the functions evaluate at xi point, and what do we have here? This is the basic functions for the Lagrange interpolations. And then this basic functions is written in this way. Is the products here, and then the j does not equals to I, x minus xj. This is the basic functions for the Lagrange interpolynomial, Lagrange polynomial. And then we have, we vary the j index here, but the j cannot be I here. So we have pxi and then xi here, but this j and this product, the j is varying, and then for the j cannot be I. And this is the Lagrange interpolations here. And so, but now what we are considering is integral. So let's do the integration here. So integrating. So we have the, let's say this is the formula 1, the equations 1, and then integrating the equations 1 over the interval -1 and 1, we get this. We get, so -1, 1, and then px dx. And then, so on the right-hand side, you have this. And then the variable is just x. So this is a constant pxi. And so we can write it in this way. So we have the sigma sum I equals to 1 to the n, because this part is just constant, so we don't need to do the equations here. We just need to do the equations for this x part, the variable, the functions with x of x. So pxi here, do the integrations over the interval, and then this one, j equals to 1. This is the basic function. And now let us do some, let us say we replace this value. So we are not going to do the integration here, but we are going to replace this expressions with 1, because after this is a definite integral, so we can get a value at the end. So we are going to replace this expressions with ci. And that is the coefficients we have here. So let us say this is a ci. This is the coefficient ci. So we can rewrite the things below here. And this is some things what we want here. This is, it looks like the quadratus we want, the quadratus rule we want. And this is how we calculate the quadratus rules coefficients. We do the integrations over -1 and 1 for that Lagrange polynomial basic function. So I think the time is off, and so we are going to continue our discussions next time. And we will show this quadratus rule has the most degrees of precisions.
I just understand this proof. So first of all, this is the very first thing to the lecture, that just the proving that the two end precisions. What's exactly the precision degree of precision of an estimation? What is that exactly?
You mean the most precisions, right?
Yes. So it was
The exactly, it means that it means that because we are using this quadratus rule to approximate that integral, right?
Yes.
Exact, it means that. So
So if
usually,
we do it on a polynomial that has degree.
so usually you are doing this way, and then you have so for example dx and then the dx, and then you are using some ci sigma sum. This is approximation.
Yes.
approximation, n I equals C1 at xi, and then this is a coefficient in terms of it.
Yes.
And so it means that exact, it means that for the, if we have a polynomial here,
That has a degree of 2n.
what is it here? That the degree. So we said this one, if the I'm
I'm
going
not
to
sure.
use,
Yeah, I
I'm
did-
having some difficulty in reading that one. So which questions are you asking?
Yeah, it was this one. So
So if this one has the degree of precision,
so like
so we are doing the proof of the contradictions. And then if you are supposing, if you are supposing the degree of precision is bigger than or equals to 2n,
yes, but
then we can. So if the degree of precision, so let's say the degrees of precision is 2n.
but does that mean that it's the polynomial we are doing it on as the like it has a like it has something like this in it?
Yes,
Okay, but
but
where
this
does
for
that
this
have that in it?
for this integral, for this function, if you expand it and then the first term you have x to n. Because you have degree 2 here, degree 2 here, degree 2 here, and then you have n expressions, so you have that degree 2n.
Oh yeah, because we start from 0. Oh, okay.
Yeah.
Okay, I get that.
Mhm.就出来吗？
对，这是为什么？
因为你这个是有2的 degree 2，对吧？你有 degree 2，也有 degree 2，那不就是 2n 吗？最大的，就相当于 x2，你不停的，就你如果是你 expand 这个东西，对不对？如果你要 expand 这个东西很简单，就是 x square 减去 2x0x 加上x0 square，对吧？这样最大的这个就是这样子，你把所有这个第一项都乘起来，不就 x2n 吗？
然后就是我们在算这个东西的时候，
对
所以我们的 null point 指的是 x1和x2，对吧？
对。
OK，
就是它就是我们有 tuner 的保证 x1 x2，然后但是我们不确定它在哪，所以我们要算它出来。
OK，好的，谢谢。
这为什么很大？
很大一定啊，因为那我刚才是这样子解释的啊，然后我怎么说的呢？那我就现在就得问了啊，那我问你哈，这个东西是什么？哦，sorry，有
没事没事继续
我要那个高光的。
哦，
这个东西是怎么样的 ？the negative 的对吧？
对，
这是 the negative 的对吧
对？
这是 the negative 的。
对。
如果是 the negative，那很难说明了哈。但是这个东西是 positive 的，就是这个微方选是 positive，但是你可以默认它是等于1了，等于1，你大于等于1，大于等于0，大于等于0。你一个方选它永远大于等于0，它的面积不就是肯定会大于0的吗？但是它如果说你说大于等于0，整个方程是大于等于0，这还是有点问题的。
对。
但是它不是恒等于0啊，因为你看它的形式就知道了，它肯定是要在上面这样子走。
但是如果有一个 x， 因为一个 x 等于0，那整个都是0，那它也不能说是。
那你看着哦，你这是一个 function， 你懂吗？你不是一个点，你看它是这样子的，你是个 function， 然后 a、b， 它是做了一些它是 x0在这，大概 x0在这 ，xn 在这，对不对？x1这是 x2， 但是它的方式是 goes like this， 这个方式是这样子走的，或者说那肯定不对的，我画的肯定不对，因为它有一些零点，所以它可能是这样子走的，你懂吗？它有零点，但不影响它的这些面积是正的，对吧？它有零点，零点就是它触碰了一下，让反弹上去了。
谢谢。
Hello. So I did number 1. Just test I did number 1, and I basically just like found the different like coefficients there in a matrix and then just solved it. like that.
Yes, it's correct.
So just like, okay.
Yeah, this is the matrix things to solve that equation.
Yeah,
linear
to solve the
equation. Yeah.
different, okay. And then I was having problems with number 2.
Mhm.
It's deriving the Simpsons rule with the
Of
Fermat polynomial. I
uh,
just am not too sure how to start that.
do you know what is the Hermite interpolations from? Let's go back to what we have in the chapter like. Well, do we have Hermite interpolations in the chapter 4, chapter 3?
I'll have to check the book, but I'm not too sure.
So once you have that polynomials, and then you just start with the. So we have 1, 2. So we have 2 notable points, and then with 2 derivatives.
Mhm.
And then that Hermite interpolation, you know, for all the interpolations polynomial here, you have that formula. You just need to plug in that formula and that get that interpolation polynomial. And then once you get that interpolation polynomial, and then you do the integrations of that interpolations of polynomial, and then you get the Simpsons rule.
Okay, so you
But
like
you need to look up
the
how
polynomial
does
itself.
this look like, yeah.
Okay, so you have that like polynomial like expansion itself, and then you like take the integral,
Yeah, do
of
the
it,
integral.
and then
Yeah.
that would give you the Simpsons rule.
Yeah.
Okay, cool. Thank you.
This is the general way we derive the Simpsons rule, trapezoidal rule, or other rules.
Okay, cool. Thank you.
老天爷，这么难的吗？